Hi everybody. We're now going to continue in Module 2 with integration as we go through our calculus primer. Here's the lesson overview. So last time we went through a couple different ways to find the zero of a complicated function. That was nice. We learned a couple ways that we'll be using throughout the rest of the course. Now we'll kind of do what goes up must come down. A couple lessons ago we reviewed derivatives. Now we're going to go the other direction. We're going to do integration. And again, this is a situation where I hope that you'll remember a lot of old friends. Let's make the fundamental definition that a function capital f of x having derivative little f of x is called the antiderivative. The antiderivative is denoted capital f of x equals the integral, that little sign there is the integral sign, of f of x dx. And it's also called the indefinite integral of little f of x. So there's a couple ways that you can say the notations. This is the fundamental theorem of calculus. If little f of x is continuous, then the area under the curve over the interval ab is denoted and given by what's called the definite integral from a to b of f of x dx, that's equal to, and this is notation, capital F of x, the big straight up thingy, evaluate a and b, that's just the way you say it. This is equal to capital F of b minus capital F of a. That's the fundamental theorem of calculus. This relates the derivative of a function capital F of x, and it relates it to the antiderivative of a little f of x. So everything's all nice, what you would expect. The reason they call it a definite integral is because it's really, really an integral. Here are some old friends. Just like we looked at the friends of the derivatives, here are the friends involving integrals. So the indefinite integral of x to the k power is x to the k plus 1 over k plus 1 plus c. C is an arbitrary constant because you'll see that when you take the derivative of x to the k plus 1 over k plus 1, that c just becomes a 0. So I'm going to have that c every place, and I'll give you a little mnemonic to remember that in a minute. This particular integral holds for all k not equal to 1. For k equal to negative 1, for k equal to negative 1, we have to look at the special case, integral of dx over x. It turns out that's the natural log of absolute value of x plus c. We'll look at a mnemonic for that in a little while. The reason for this is there's some convergence and divergence issues which only take place when k equals minus 1. So let's just remember that. Now, if the derivative of e to the x is e to the x, then the integral of e to the x dx is e to the x plus c. Similarly, the integral of cosine equals sine plus c, because remember when we took the derivative of sine, we got cosine. And the integral of 1 over 1 plus x squared is equal to arctan plus c. So these are just, there's a million of these things, and I just gave a few that you might remember. Here's an example, and this is that mnemonic I was talking about. It's very easy to see from the previous argument that since the integral of dx over x is log of x, then the integral of d cabin over cabin is log cabin. Pretty funny math joke. But the reason I'm giving you this is because I want you to remember that plus c, the arbitrary constant. And then we remember that the log cabin plus c is equal to houseboat. So that's just something to keep in mind, and I'm sure you'll remember that the rest of your lives. Theorem. Some well-known properties of definite integrals are as follows. The integral of f of x dx from a to a, so think of the area under this continuous function over under one point, there is no area, so it's 0. The integral from a to b is negative of the integral from b to a. And finally, the integral from a to b plus the integral equals the integral from a to c plus the integral from c to b. So if you stop taking the integral at some midpoint c, and then you start up again, when you add those two pieces up, you just get the whole thing from a to b. Here are some other properties of general integrals. The integral of the sum is the sum of the integrals. This is sort of the analogous to the product rule in derivatives, and this is called integration by parts. Integral of f times g prime equals f of x times g of x minus the integral of g times f prime. That's called integration by parts because we're breaking things up into f and g. And finally, this is sort of reminiscent of the chain rule. The integral of f of g of x times g prime is equal to f of u du. That's the substitution rule where we take u equal to g of x. We've got to be a little bit careful here because this substitution of u of x equal to g of x will possibly change the limits of integration. But it's something that you should remember. And here's a couple mnemonics that will help you remember. You can go look them up on the web. Let's use integration by parts with f of x equal to x and g prime of x equal to e to the 2x. And then we'll also use the chain rule as well. So integral of x times e to the 2x. So this thing, you can see that I'm associating x with f of x and e to the 2x with g prime of x. When you use this integration by parts, one of the tricks is just figuring out what's the f of x part, what's the g prime of x part. So, according to integration by parts, the first term is going to be f of x times g of x, which is f of x is x, g of x, the integral of g prime, which is integral of e to the 2x, is going to be e to the 2x over 2. I needed the chain rule for that. So that first term, x times e to the 2x over 2, evaluated 0 and 1. And then subtract off g of x times f prime of x. And g of x is e to the 2x over 2, f prime equals 1. And so what I have, I do my substitution of 0 and 1 into that first term with the big vertical thingy. Then I subtract off the integral, and I get e squared over 2 after I substitute. Now I do the integral. That turns out to be minus e to the 2x over 4, evaluated at 0 and 1. And there's my answer, e to the e squared plus 1 over 4 when the smoke clears. So a pretty easy example. Let's give another definition. Derivatives of arbitrary order k can be written as fk in parentheses of x, or dk dxk f of x. And by convention, we let f naught just be the same as f of x. So one nice thing, which we'll use a couple times in class, is that you can write f of x in what's called a Taylor series expansion about a point A. And it's given by this infinite sum from k equal to 0, of the kth derivative evaluated at a times x minus a to the kth power over k factorial. That's what's called a Taylor series expansion, and it's quite nice. It's used occasionally. The Maclaurin series is just the Taylor series expanded around a equals 0. Now, without going into huge detail, here are some Maclaurin friends. You may remember this. Sine of x, if I do all those derivatives in the previous slide, can be written as that infinite sum, the first one, cosine of x, the second infinite sum, and e to the x is the third one. They all look a little messy, but they're really not bad at all. And they're actually kind of famous. And while we're at it, because I'm looking at all these sums, here are three that have nothing to do with these Taylor series, really. But these are just things that come up every once in a while, so this is as good a place as any to talk about them. If I'm interested in adding up all the values of k from 1 to n, that's just n times n plus 1 over 2. This is something that Gauss was able to do when he was 5 or 6 years old, believe it or not. If I want to add up all the values of k squared, you get n times n plus 1 times 2n plus 1 over 6. That's famous. And if I have this infinite geometric series, I want to add up p to the k from k equals 0 to infinity. It turns out that that's just 1 over 1 minus p. That's something that you probably learned in high school, but it bears repeating. So one last thing we'll talk about is L'Hopital's rule. Every once in a while, we get into trouble when we have something of the form 0 over 0 or infinity over infinity. So sometimes L'Hopital's rule is useful because it turns out that 0 over 0 or infinity over infinity, they could equal anything. So here's what it says. If the limits f of x as x goes to a and g of x as x goes to a both go to 0 or go to infinity, then the limit of x goes to a, the limit as x goes to a of f of x over g of x equals the limit as x goes to a of f prime of x over g prime of x. And it looks like we're complicating things, but sometimes this rule, L'Hopital's rule, makes things a lot easier. And this rule makes me sick, ha ha ha, L'Hopital. So here's a quick example, and this characterizes why this thing's so useful. So let's look at sine of x over x. Now, as x goes to 0, this is a 0 over 0 type thing. So it turns out, let's take the derivative. Derivative of the top, sine of x, is cosine of x. The derivative of the bottom, x, is equal to 1. So I can now take the limit as x goes to 0 of cosine of x over 1, going to be cosine of 0 over 1, which is 1. So congratulations, you've just shown sine of x over x goes to 1. Again, got to be a little careful because these 0 over 0 things or infinity over infinity can go to any quantity. You've got to be very careful about that. Here's a summary of what we just did. We've renewed acquaintances with a bunch of old integral friends, and we looked at some elementary properties, including L'Hopital's rule. Next time, I'm going to look at some numerical integration techniques, and I want to see what happens when I can't do the integrals in those nice closed form. So what do we do if those friends don't want to come out and play with us? And anyway, we'll see you next time.